Hello, and welcome back. In this video, we will be applying the arc length formula to planetary objects. In particular, we're going to be working out a formula or a way of computing how far a planet actually travels when it makes one revolution about the sun. Now, if you're working through the activity problems, and if you're in the class, you should be working through these activity problems. Last week, the objective was to show that a planet revolves around the sun in an elliptic orbit, right? This is one of Kepler's laws. So what we're really asking here, what the bigger question is what's the arc length of an ellipse? So an ellipse can be described in this vector equation, or vector valued function rather. And here, yeah, we'll assume the semi-major axis is along the x-axis and b is the semi-minor axis, and we can describe it with this. Now, for these calculations, it's going to be helpful to keep in mind this ratio of the semi-minor axis to the semi-major axis. So that's b over a. I want to keep this ratio in mind. I'll use this later on because we want to show that this has a certain form. And so, all right, let's find the arc length of this ellipse. All right, so here's my ellipse just drawn sort of quickly there. We're finding the length of this curve. One thing to notice here is that there is some symmetry with an ellipse. So if I can actually just integrate from here to there between these time values and get the length of this curve, then it's really just 4 of those to give me the length of all the curves. Right, so if like this is L1 and the whole curve is L, let's say the whole curve is L, then L is 4 L1, right? So there's some symmetry, so I just need to integrate between those. That'll be helpful later on. All right, so I know that to compute this length as it travels around, I'm going to be integrating from 0 to 2 pi as it travels around this. Right, that was how our vector valued function for this was defined, from 0 to 2 pi. And I want to integrate the speed. So I'll use r prime of t here. I could use v, it's fine. R prime of t. So that's my objective. Again, my helpful piece of advice almost through this entire class is break down these multi-step problems into component parts. You're less likely to make mistakes, and if you do make a mistake, it's a lot more helpful to figure out where your mistake was made if you break it into parts. So I'll remind myself of what my r of t is. That was the a cosine t, b sine t, and then r prime of t will be, what, minus a sine t and b cosine t. We've been doing this one quite a bit, right? These derivatives should be very familiar by now. And then if we want the magnitude of that, well, that is square root of a squared sine squared t plus b squared cosine squared t. So this is the integral. Actually, let me go. Yeah, I'll go there. All right, integral from 0 to 2 pi. Remember, that's t values of square root a squared sine squared plus b squared cosine squared. All right, so notice, yeah, we don't, if this were a circle, if a was equal to b, we could factor that out and we just have a constant here. That's right, that's what happens when we do this for a circle. But since it's an ellipse, we have this a squared and this b squared. So here's where I'm going to play a little bit of trickery to get this into another form that has a name, right? Is the idea is to get this into an integral. Remember, integrals are not always so easy. Even definite integrals, we can't always find an expression for them easily, but rather we have to resort to analytic methods for this, or like computational methods for finding approximations for this thing. So that's the idea with this one, because this is not an easy integral to solve. In fact, yeah, we can't solve it. We need analytic methods. So I want to get it into this form. So what I'm going to do is I'm going to divide everything through by a squared yeah, so I'm going to pull out a squared. 0 to 2 pi. I'm going to write it like this first and then talk about something. So I'm pulling out an a squared there. And so what I'll get here, I'll just get sine squared t plus b squared over a squared cosine squared t. dt. So now, right, I can pull this a squared out of the root as just a, because a is a positive quantity. So this is going to be a times 0 to 2 pi of square root of sine squared t plus, and then this is alpha squared, right? Remember, alpha is b over a. I defined that earlier as this ratio. So this is alpha squared plus alpha squared cosine squared t. And then last thing I'll do here is I'm just going to consider the quarter of this. So this is the full planetary orbit, and remember that this length was just 4 times one of these quarters, right? So I just want to do a quarter. That's just going to make the job a little bit simpler, especially when I'm using numerical methods to solve it. So I'll actually just consider this as 0 to pi over 2, and that's my square root sine squared t plus alpha cosine squared t. And this thing, so now we have this thing, we can't, yeah, like I said, we can't solve this with elementary functions for sure. And so we use numerical methods on this. What this is called is an elliptic integral. Elliptic integral. And there are several different kinds of elliptic integrals that you might come across when you're doing this sorts of things with ellipses, calculus of ellipses. And so this is called an elliptic integral of the second kind. I don't know, maybe there's a joke there about close encounters of the third kind. I don't know, something like that. Elliptic integral of the second kind. And so to solve something like this, well, we live in the day and age when we have access to free computational engines, such as Wolfram Alpha, will solve these for you, or if you have access to Maple or any sort of computer algebra system, they'll likely have some function for an elliptic integral of the second kind. Right, so this is a little bit unsatisfying because we can't compute it directly. That's okay, though. We still want to know what are the lengths of the planetary orbit. So just a note on that. So we'll use this to solve it. And then what we can do is we can observe these heavenly bodies as they move around the sun. And we can work out what these axes are. Right, like what's my semi-major or my semi-minor. I can compute my alpha. And then I can go and run this. I can actually, computationally find this integral. And so 1 astronomical unit, right, is the distance between the Earth and the Sun. And so, right, we can now measure length of planetary orbits. And we'll put it in reference of distance between the Earth and the Sun. So Neptune's way out there. One thing that's sort of interesting when looking at this chart is how close alpha is to being 1. Right, if alpha is 1, that means b is equal to a. So this is a measure of how close the ellipse is to being a circle. It's 1 if and only if it's a circle. And so this is rounded to 3 decimal places. We get 1.000. It's not exactly 1. It's not, right? There's no way it's exactly perfectly a circle, but to at least 3 decimal places, it's 1. It's basically a circle. So yeah, the planets, we've been told they don't go around in circles, they go around ellipses, but really this is kind of expressing how subtle that effect is. They're very close to being circles, but technically ellipses. And so it's harder to work out their orbit length. Okay, that's it for this video. I'll see you next time.